Okay, so before we get started, just a quick announcement. So there will be a quiz for this week. So I'll be covering the material we covered this week about the glomerulus and filtration. There are also a couple questions from last week when we didn't have a quiz. So a little bit on water balance there. For next week, Dr. Schlater and I are both out at a conference on Monday. So what I'm going to do for our schedule, we're going to keep the exam on the date it is, but I'm going to give you guys the review materials early. So on Monday, what I'm going to ask you to do is work through the review materials. And then on Wednesday, we'll have one more sort of short topic. And at the end of that lecture, I'll tell you like what exact sort of 3 question types you might expect from that last segment of material. Just because otherwise this amount of material that we've covered thus far in the renal unit is pretty short. And while that might seem like a good thing for an exam, I'm a little worried that if we cut too much of it, that we'll have to get into some like very detailed nitty-gritty questions, which is, I think, not necessarily to your benefit. Okay. So Monday, you'll be working on review materials. On Wednesday, we'll have one final little chunk of material. I'll be very clear at the end about what you might expect to see in terms of questions from that additional chunk. So I believe this is where we left off when we were talking on Wednesday. So we're talking about glomerular filtration, right? Right? A bunch of related concepts. So we're thinking about how we can control the glomerulus and how much blood is flowing into it, how much plasma is flowing through it in order to control how much fluid is being filtered out through the kidneys overall. So we saw that this is related to mean arterial pressure. So blood pressure does have an effect on this, because if your blood pressure goes up, that means you have essentially more plasma moving through the glomerulus, so through this first part of the nephron, unless we constrict those arterioles, preventing quite so much blood from getting there. So at very high ends of our mean arterial pressure, we start to see sort of runaway filtration rates. At very low blood pressure, we start to see that because not enough blood is getting to the glomerulus, basically, it's not exerting enough pressure on those capillary walls. Remember that hydrostatic pressure of the blood in the glomerular capillaries is pushing out into Bowman's capsule. That's one of our 4 Starling's forces, and it's really the main one driving filtration, so driving the movement of fluid from the blood in the glomerular capillaries into the filtrate in the nephron. Okay. So pressure has an effect. The blood pressure has an effect on that hydrostatic pressure. So if we're outside the zone within which we can kind of regulate and keep things stable, we start to see a sort of a linear kind of relationship between the mean arterial pressure and the glomerular filtration. So what we're looking at here is basically when we're talking about our regulatory mechanisms that involve the afferent and efferent arterioles going into and out of the glomerulus, and those juxtaglomerular cells that are able to, in different ways, force our arterioles to constrict and therefore regulate pressure in the glomerulus. We do also see responses to low blood volume and low blood pressure. Okay. So the other regulatory mechanisms we were looking at were mainly responses to high blood pressure, but we do also have responses to drops in pressure. Okay. So a lot of this diagram is things we talked about when we talked about the heart and when we talked about the cardiovascular system. So things like hemorrhage, right? If you're bleeding out, you're really, really sweating hard. When you're losing a lot of fluid, this can drop your blood volume because ultimately that fluid is coming out of your blood. That's where the water is coming from. This drops your venous pressure. Right? So as you drop your venous pressure, that means less venous blood is returning to your heart, which means that when your heart beats, there's less cardiac output, there's less blood coming out of it, which means your mean arterial pressure drops. right? So that's the heart part. Okay? So this is all something that happens when we have a drop in blood volume. When we talked about the cardiovascular system, we learned that there are baroreceptors, so pressure receptors that detect and respond to this drop in pressure, right? And what maybe you remember, hopefully you remember, is that one of the responses to this drop in pressure, that's part of this thing called the baroreceptor reflex, is that we have a jump in sympathetic nervous activity in response to this drop in pressure. So when your body senses maybe you lost a bunch of blood volume, you've lost a bunch of mean arterial pressure, the sympathetic nervous system gets activated, so it starts firing more. This means that sympathetic nerves going through your kidney also are going to be firing more. So we're going to see increased sympathetic nervous activity in the renal system. So our renal sympathetic nervous activity goes up. And the effect of those sympathetic nerves in your kidneys is that they are going to do vasoconstriction, right, of our afferent and efferent arterioles, which is going to increase our vascular resistance. Okay. And one effect here is that we're going to be decreasing our glomerular filtration rate, which means we're going to be decreasing our urine flow, which means we're preventing fluid loss. So that fluid is staying in the plasma, which means that we're going to keep our remaining blood, our remaining fluid in the blood, keeping the blood volume up here. Okay. We can also trace other sort of pathways through here. So another thing we see is that that drop in blood pressure, it does create this sort of sympathetic nervous pathway, but it also does just quite directly lower glomerular filtration rate, because that drop in pressure means there's a drop in the hydrostatic pressure of the plasma in the glomerular capillaries. We can also see that there is a negative feedback loop happening as well. So as we raise vascular resistance in the kidneys, well, our total peripheral resistance is something we care about when we care about the cardiovascular system. So raising that renal vascular resistance is raising our total peripheral resistance and raising our mean arterial pressure. We have a lot of different things going on here. But basically the sum of it, what you want to know is that we do react to drops in blood volume and drops in blood pressure by decreasing our fluid loss, partially using the activity of the sympathetic nervous system so that we can keep blood volume up. That's ultimately kind of the point here. So if you get lost in the middle, I would focus on like what our initial stimulus is and what our result is. And then I'm just going to pick out that you want to know that this has something to do with the baroreceptors and the sympathetic nervous system. So I would consider those like the important pieces here. So what we were talking about on Wednesday and that last little explanation in that flow chart, we're talking about filtration, control of filtration, right? So filtration, just a reminder, is movement from, this is our glomerulus, this is Bowman's capsule. So filtration was movement from the glomerular capillaries into space inside of Bowman's capsule. So that was filtration. So our next bit we're going to talk about is reabsorption, which we have talked about a little bit as we talk about water. So reabsorption means that we're thinking about fluid that has already been filtered, right? Like it's already moved from the glomerulus into the nephron, right? So that already happened, filtration. Now reabsorption means we're moving from the tubules, from that filtrate, back into the bloodstream. So the part of the bloodstream that we're going to see here that we can get into is those peritubular capillaries. Peritubular just meaning next to the tubes. Right, so all that's saying is that after the plasma goes into the glomerulus, it keeps flowing, right? And then we start to have peritubular capillaries neighboring the rest of the nephron. Most of our reabsorption is happening in the proximal tubules, and most of it is not regulated, as we learned when we talked about how water moves across the proximal tubules. So we can see that there are normal rates of filtration and reabsorption for water and any kind of solute you can think of pretty much. So we can see that especially where we're going to see that we have a lot of reabsorption of, we have water. So more than 99% of our water is getting filtered and then reabsorbed. Another thing we see quite high, we have a lot of sodium reabsorption. So sodium is in your plasma, it's getting filtered into the nephron, and then you're mostly reabsorbing that sodium. So you can continue to use it in like sodium potassium pumps elsewhere in the body. We know that sodium is really critical for nervous function, right? As we talked about action potentials. So we need most of that sodium. Lots of our things we are reabsorbing, right? A lot of these ions. But one thing that particularly sticks out is that under normal conditions, 100% of our glucose should be reabsorbed. You should not be peeing out energy, basically. So if your kidneys are functioning normally, you do move glucose with all that rest of the plasma, everything except the proteins, into the nephron, but then you should be reabsorbing it so that you can keep that glucose for energy for your body. So if you see glucose in someone's urine, that's kind of indicative of a problem. So we talk about water reabsorption, but we can also think about solute reabsorption. Right? So most of the solute reabsorption, like most of our water reabsorption, is happening in the proximal convoluted tubules. So they're proximal tubules, proximal convoluted tubules. There's not really a difference in that terminology there. They're talking about the same thing. A little bit of the solute reabsorption is happening in the distal convoluted tubule as well. And we can think about what our barrier for reabsorption is. So like what layers do we have to get through to move a solute from the filtrate back into the blood? Well, we're going to have to go through the cells lining the tubule. Those are our epithelial cells of the renal tubule. We have a little basement membrane. There's some peritubular space, but the other cell thing that we're going through are our endothelial cells in the capillaries, right? So these are the layers we're going across. We can just remember how to name the different parts of these epithelial cells that we saw, right? So our basolateral side is the side that's towards our capillary. Our apical side has lots of these projections, these microvilli to increase surface area. Apical is facing the lumen. Lumen is just like the hollow part. Oh, it is labeled at the bottom. So our reabsorption is going to move all the way from the filtrate, so from inside our tubule, all the way into our capillaries, all the way into our blood. So we filter out 180 liters of water per day, but only about 1 or 2 liters is excreted as urine, which means we're reabsorbing a ton of water. We looked at how that works. So most of the reabsorption is happening in the proximal tubules. It's at 70% in the proximal tubules. A little bit is happening in the descending loop of Henle. So that part is unregulated, but we know that the really important thing about the loop of Henle as we descend into the medulla of the kidneys is that we're setting up that osmotic gradient. We're setting up that increasing concentration of solutes as we get deeper into the kidney, which means we exert more and more of a pull on the water that's remaining in the tubules. which means that we are able to regulate the amount of fluid that gets reabsorbed in the later parts of the nephron. So from the distal convoluted tubules and the collecting ducts, we know we can control whether those epithelial cells, whether they allow water through them or not, so whether they are permeable to water or not, by either inserting aquaporin tubes on that apical membrane or not inserting them there. So that's our action of antidiuretic hormone that we talked about before. Okay, so that was all our water reabsorption stuff. So usually our osmolality of the filtrate in the glomerular capsule, so in that Bowman space, and that Bowman capsule is going to be isoosmotic with blood plasma. So we said that we're going to start out at 300 milliosmoles. Okay. Sodium is going to be actively transported out of our filtrate and into the peritubular blood, so into those capillaries alongside, in order to set up a concentration gradient that drives osmosis. Right, so we said that we're moving sodium across. Right, we move sodium into our bloodstream so that water then follows along with it because it's drawn to this higher sodium concentration that we're setting up. So that's one of the reasons we are actively going to transport sodium. All right. So reminder of what the sort of structure of these cells looks like. So we labeled apical side, which we think of as top, with that microvilli, those projections increasing the surface area, versus the basolateral membrane, bottom facing the blood. Right. So they're connected by tight junctions, which is a type of cell junction that basically prevents paracellular transport, prevents molecules from going between cells and not having to cross membranes. So we have these tight junctions in the epithelial cells of the kidney. Okay. What we would notice about the inside of these cells, right, we talked in our water section about the fact that we have sodium-potassium pumps. Basically, on the basolateral side, we have sodium-potassium pumps here, pumping sodium out and potassium in, which means that we have low sodium concentration in these cells so that they start to draw sodium out of the filtrate. So we could say low sodium. I realize that this is all just a sort of different picture and different slide repeating the same thing that we talked about when we talked about water to this point. So low sodium here, high sodium here, means we draw the sodium into the cell and then we're actively pumping it across the basolateral membrane so that we can pull water alongside. This also has an effect on chloride ions, right? So this is slightly different than how it's affecting water. So when we talk about the sodium moving and drawing the water along with it, that has to do with the fact that we're building up solute concentration and osmolarity on the opposite side of this cell membrane, right? So we're building up solute concentration over here in the peritubular space and essentially kind of in this blood as well. What's going on with the chloride ions is that this has to do with their charges. So the chloride ions are negative, our sodium ions are positive. So that electric charge is drawing chloride ions out of the filtrate to follow along with the sodium ions. Right. So far we have sodium ions, right, chloride ions, and water are all being reabsorbed here in the proximal tubule. The one that we were doing active transport of, right, because we talked about that pump, is the sodium. Both the water and the chloride are moving passively The chloride ions are moving because of that electrical charge. The water is moving because of that change in osmolarity. So it's moving by osmosis. Active. And then this part is passive. It does say this on the top of the slides. I'm just highlighting it for you because I think it's easier to kind of pull these things together as we go. So this is just an image looking at these things. I don't really know why your book insists on renaming our solutes X, Y, and Z, but I guess the idea is that this is generalizable as well, although really what we're talking about is the sodium, the chloride, and the water. So whenever you look at diagrams of nephrons, you can get diagrams that tell you what is crossing the membrane in which section of the nephron, and I do recommend that you consult those and study those because it's basically a really good summary of how the nephron works, and it's really the basics of what you need to know. But what we're seeing here is just kind of the beginning of what a diagram of that might look like. So we see filtration. We have kind of everything moving except for proteins into the nephron. And so now we're looking at the proximal tubule. We see that we have passive transport of chloride ions, osmosis of water, which is a type of passive transport, active transport of sodium ions. And then down at the bottom, it's telling us that the effect is that we're reducing the volume of the filtrate. So this fluid that's ultimately going to become urine, it's filtrate, we're reducing it to about 1/3 of that original volume because we're reabsorbing so much of the water. But at this point, it's still isoosmotic. So we still have the same osmolarity inside the tubule versus outside because we've moved both solutes, the sodium and the chloride, and water, and they're balancing each other out at this point, basically. So we haven't changed the overall osmolarity here. This brings us to the idea of transport maximums, which are going to be important specifically when we talk about glucose. And thinking about glucose really is one of the main things we think about when we think about pathology in the kidney, just because diabetes is so common, and poor handling of glucose in the kidneys is one of the ways you could diagnose that, or one of the things you might be monitoring in certain patients. Okay, so the way we move things across membranes, just a quick reminder, right? So we have a membrane. The way you get stuff across it, if it can't cross on its own, right? So if it's too big, if it's charged, those are basically the main two reasons, is you need to have an embedded protein in the membrane, which we call a carrier, right? So when we're talking about the transport maximum, what we're saying is that there's a certain rate of transport, like an amount of a molecule we can move across the membrane that fills up all of the carriers in that membrane. And we kind of talked about this way back at the beginning when we talked about enzymes, and we talked about the fact that you could fully saturate all the enzymes you have present. It was probably in September. But the basic idea hopefully isn't too bad, right? You only have a certain number of carrier proteins in a membrane. At a certain point, they're all going to be full. They're all going to be doing stuff, which means there is a maximum rate at which you can transport a substance because you just don't have any more space after that. So that rate, when we have the carriers fully saturated, we call the transport maximum. Transport maximum is that maximum amount that we can be moving. The renal threshold for a solute that is normally 100% reabsorbed is related to this concept, right? So when we say the renal threshold, we're saying basically like the amount that we can handle going into the kidney, into the filtrate, before we're going to have spillover. So if we're thinking about glucose, it has a renal threshold, and we'll look at the graph of where that is. And if we're below the renal threshold for glucose, our glucose is lower than our renal threshold, this glucose is going to get 100% reabsorbed. But if we reach or exceed the renal threshold, we're going to see that we are at our transport maximum or above our transport maximum, meaning all those carrier proteins are going to be full. They're not going to have any more capacity to handle more glucose because they're already busy, which means you're going to see some of that glucose remaining in the filtrate and therefore showing up in the urine. So for glucose, usually freely filtered at the glomerulus, meaning because of the big pores in those fenestrated capillaries and because of the structure of the glomerulus, glucose can just move on through like everything else in the plasma. There's no significant barrier to glucose moving from the plasma into the filtrate at the glomerulus. And in the proximal tubules, it's normally 100% reabsorbed. This is an active process, so it does require energy, but your body does it. So normally no glucose is going to appear in your urine. But this active reabsorption is dependent on carrier proteins. So at the apical membrane, we see that glucose is crossing that membrane by secondary active transport, and we'll take a look at that in a second. And then on the basolateral membrane, it's moving by facilitated diffusion. This means that those carrier proteins that are necessary, if they're full, if we occupy all of them, we're not going to be able to soak up any more glucose. Yeah, got a picture. Okay, so what we see here, right, is that movement of glucose. And this may look, ooh, you who took bio of the cell, this figure may look a little familiar to you. So what we see happening here, secondary active transport of glucose, right? So active transport of glucose, and the way we're actively transporting that glucose is by using the gradient of a second molecule, in this case, sodium. Sodium does a lot of jobs in our body. It's regularly used for secondary active transport. So we see glucose is using that sodium gradient to get into the epithelial cell. We have a sodium potassium pump, keeping that sodium gradient steady. So making sure we always have low sodium in this cell, no matter how much sodium has moved into it. So just sort of maintaining that gradient. But now that the glucose is in the cell, it now has a high concentration of glucose in the cell, so it can move down its gradient passively from the basolateral membrane into the blood. So if we were to just look at the glucose gradient, we would say it's kind of low relatively in the filtrate. It's high inside the cell, inside this epithelial cell, which is why we need to actively transport it, right? Active transport means we're moving against its gradient. But then it's low over here in the plasma, so we can just move passively down the gradient once we're into this cell. So that's like physically what the glucose is doing. If we think about its renal handling, your normal concentration of glucose in the plasma is about 100 milligrams per deciliter. Your filtered load, remember we're multiplying times our glomerular filtration rate to get our filtered load, right? We multiply it basically a concentration times, yeah, the glomerular filtration rate tells us that our filtered load for glucose is 125 milligrams per minute. That's how much glucose is getting into our nephron per minute, into the kidney. Our transport maximum is 375 milligrams per minute. So our transport maximum, the fastest we can move glucose, the fastest we can reabsorb it, is 375 milligrams per minute. And if we did the calculations out, that means that at a concentration of 300 milligrams per deciliter in the blood, that is where we would hit that transport maximum. So it might be helpful for me to clarify, just because these two terms are very similar, right? So note that the transport maximum is talking a rate. So this is our milligrams per minute versus our renal threshold is talking about an amount. So this is milligrams per deciliter. These two concepts are essentially the same, the transport maximum and the renal threshold. They're both talking about like what is the maximum amount of glucose in this case that we can process. It's just one is telling you the speed with which we can process it, and one is telling you like a concentration where you're going to have trouble processing it. But the cause of having a transport maximum in the first place is that carriers get saturated, and that's the same thing for the renal threshold. There's a renal threshold because above a certain amount, those carriers get saturated. So they're really kind of just different measurements of the same thing. So our renal threshold, we wanted to relate these two things. You multiply renal threshold and amount by your glomerular filtration rate. That's a rate, and that's how it would be related to the transport maximum, which is then also a rate because we added in the time component here with the glomerular filtration. So theoretically, we can handle 300 milligrams per deciliter of glucose in our blood. But if you're actually in clinic, that's not very realistic. There is an actual renal threshold that is much lower than our theoretical renal threshold. And the reasoning for this is basically what we're talking about, right, is glucose flowing in a fluid past these cells that have these carrier proteins in them, right? So our theoretical renal threshold says, okay, every single carrier is occupied with a glucose molecule. But because of this movement of fluid, like the fluid is not stopping and carefully inserting a glucose in every carrier, it just keeps moving. So it just happens that in real life, as we have this movement, for the actual threshold, some of those carriers are just going to be unoccupied by pure chance, basically by probability, because this fluid is moving past and glucose didn't happen to bump into it. But for your body functionally, it's still as if they're fully saturated because you still have glucose just like kind of moving by that carrier. It's not like you can push the glucose backwards into it. Okay. So they both have to do with saturation. This is the theoretical one is literally if you count them all up and absolutely everyone is occupied. The actual observed renal threshold is a little bit lower because sometimes some of them are going to be empty, but they're still not basically going to do us any good. So theoretically, you could handle 300 milligrams per deciliter, but in actuality, it's really about 160 to 180 is the range that we can handle before we start to see glucose spill over into the urine. And that goes hand in hand with a filtered load of 225 milligrams per minute. So that's a different load than we saw for our transport maximum. So that's also lower. So we can compare these concepts here. And I will note that what they have labeled as the renal threshold here is the actual renal threshold rather than the theoretical renal threshold. So here it's showing that's that like 180 renal threshold. So no matter what, none of these things affect filtration because filtration is just movement from the plasma in the glomerular capillaries into Bowman's space in that renal corpuscle, so in that first part of the nephron, right? None of that requires any carrier proteins, so none of this matters for filtration. It does matter for reabsorption, right? So what we're saying is at a certain point, those carrier proteins, in this case, they're carrier proteins that do the secondary active transport of glucose using that sodium gradient, right? That's the molecule we're actually talking about. They get fully occupied, right? So at our actual observed renal threshold that we've labeled here on 180, we see that that's the point at which we start to see reabsorption kind of tapering off, right? It may still be increasing a bit, but it's not going linearly with filtration anymore. Okay. So that's what's happening with the reabsorption. At a certain point, we really are at the transport maximum, and then we're just going to see an absolute flat line, not even any tiny incremental increases. And we'll see that the reabsorption line is like the inverse of our excretion line. So kind of like if you added these together, you'd get something similar to your filtration line, right? Because anything that isn't getting reabsorbed, right? So this difference, it's getting excreted, right? So the difference between the amount that's filtered and the amount that's reabsorbed is the amount that gets excreted in your urine. So those two sections should be basically the same. So as you occupy all those carriers, you get more and more glucose spillover in the urine. So next we have secretion. So secretion is going to be the opposite of reabsorption. What we're saying when we say we have secretion, we're saying we have a molecule in the peritubular capillaries, so in the blood, and we're pushing it into the tubules, right? So the solute is moving from the peritubular capillaries into the tubules. The barriers are the same as for reabsorption, so we have those epithelial cells lining our tubules. We have a basement membrane, we have a peritubular space, and then we have the endothelial cells of the capillary. The mechanisms we use for secretion are going to be the same, right? So mechanisms we use for transport throughout the body are kind of the same, right? We always have, some carriers, potentially some pumps, right? Various types of membrane proteins. The substances we're going to be secreting are mainly some ions, right? So potassium and hydrogen ions are going to get secreted, but we're also going to see some other things. So choline, creatinine, and penicillin. So drugs may be secreted here as well. So these are things you could observe in the urine as well, right? So if you secrete something, move it from the blood into the nephron. That means it's in the filtrate now, which means you're going to be able to observe it in the urine. So here we're looking at a whole nephron again. We're going to think a little bit more about specialization. So our key thing that we think about when we think about proximal tubules is really we're not regulating reabsorption. So we do have some active transport, right? We did active transport of sodium using that pump, and we did secondary active transport of glucose. So what I want to just emphasize to you is that active transport doesn't mean it's regulated. Just, I don't know, those words are something similar in people's heads. Non-regulated means we're not using hormones to adjust this, basically. You don't see hormones adjusting this, you don't see nerves adjusting this. Right? It's just a process that's happening, right? So it doesn't mean it doesn't require energy. It means it doesn't require like external information. So in the proximal tubules, we have non-regulated reabsorption of glucose, of sodium, of water. In the distal tubules and in the collecting duct, so at the end, right? So we have our glomerulus, we have Bowman's capsule. Put this together is the renal corpuscle. We had our proximal tubule, we had our loop of Henle, and we have our distal tubule and our collecting ducts. So the place we see regulated reabsorption happening is in the distal tubule and the collecting ducts. We know that that's really specifically the role of ADH, helping us regulate water. And we'll talk a little bit probably on Wednesday about regulation of sodium and potassium. And we know that the special thing about the loop of Henle is that we're creating that medullary osmotic gradient by pumping are solutes pumping ions from the ascending limb actively, creating an osmotic gradient that then helps us conserve water as water is able to move across the descending limb into the medulla on that side because of this osmotic gradient we've set up. So this is just a sort of cheat sheet of what is getting reabsorbed where and what is getting secreted where. So you'll notice we didn't dive into the secretion. We'll talk a little bit about this when we talk about acid base, which will be in our next unit at this point. But hydrogen ions are one of the main things we're going to think about when we think about secretion, because hydrogen ions are inextricably linked to pH, right? Like I think that's what the H of pH is. Bless you. Bless you. Our proximal tubule, the mass reabsorber, 70% of the sodium and water, which we've traced, and then 100% of the glucose should be reabsorbed in the proximal tubule. One of the specializations that allows the proximal tubule to absorb all this stuff is it has a brush border. So we keep drawing it with all these squiggles on the apical membrane because those are our microvilli, creating a brush border. So like if you're looking at a brush, right, that's what it would look like if you're looking down on a layer of these cells. And the effect that this is giving us is we have a really large surface area, which is great because transport relies on our molecules bumping into the membrane and being able to cross. So having more membrane makes it more likely that our molecules will bump into it. And we have tight junctions, which allow a little bit of paracellular transport for some things, but don't allow everything to cross. We do have sodium having to go across the cells, for example. So here's just a zoomed in image. Okay. When we get to the distal tubules and the collecting ducts, we do see regulated transport. So those tight junctions really get much tighter here in the distal tubules and the collecting ducts. We'll note that the apical membrane here doesn't have that nice pretty brush border anymore. It does have some projections, but we have less surface area here in the distal tubules and the collecting ducts if we're looking at these cells. Zoomed in picture of the epithelium. So Henley, its job is to set up that osmotic gradient that we talked about that's going to let us conserve water, right? So it's setting up this osmotic gradient so that we have a really strong force for us to be able to pull water out of the filtrate, so out of this fluid that's going to become urine and back into the body. We wouldn't be able to do that unless we had this big concentration of solutes somewhere to act as the draw. So the loop of Henle is establishing that osmotic gradient, which is what allows us to reabsorb water, ultimately in the collecting ducts in the distal tubules. This way we're minimizing water loss, right? We're not peeing out 180 liters a day. So we reabsorbed a lot of it in the proximal tubule, and then through the action of ADH and controlling the permeability of these membranes, we can control how much of the remainder gets conserved in the body versus excreted out as urine. So that leaves us with one more topic kind of in this packet. So just to review what we talked about, basically we started with filtration. So we talked about filtration is movement from the glomerular capillaries into the nephron, and it's under the control first of the four Starling's forces. So the hydrostatic pressure of the glomerular capillary and the hydrostatic pressure of Bowman's space versus the oncotic pressure of the glomerular capillaries and the oncotic pressure in Bowman's space. So those are the 4 factors we pay attention to figure out our filtration pressure, or glomerular filtration pressure, and therefore our glomerular filtration rate. And we had reabsorption. And reabsorption happens for both water and solutes, and it's the movement of fluid and solutes from the filtrate back into the plasma. That's why it's going back into the plasma. It's already been filtered, now it's coming back into our body. Okay. So we're reabsorbing a lot of things, but the main ones we focus on are water, sodium, glucose. We saw that there was a long list, but those are 3 to be particularly paying attention to. Maybe add on chloride ions. We know that secretion exists, although we haven't gotten into the details. Secretion. So secretion is what's happening if later on we have something move from that peritubular capillary into the nephron, into the filtrate, kind of through a sidewall, rather than coming originally from the plasma in the glomerulus. And then excretion is just fluid leaving your body, basically. So excretion is basically going to be urination in this case when we're thinking about the kidneys. So we're going to leave off there. So I'll put up some study materials for you to go through on Monday. And I'll have a couple of short topics on Wednesday. I may cut down some of these slides for that, I'll let you know.